So today I'm going to be talking a little bit about a basic introduction to electrochemistry, which you should be studying at least a little bit in your lecture class this semester, but you might or might not have gotten there yet. It's the kind of thing that people don't always cover a lot of, quite frankly, in their general chemistry lectures. So the reason I like electrochemistry, well, I'm an electrochemist, first of all, so I really do like electrochemistry, is that it's specific to the oxidation state of your species. I can write. So that means it's going to tell you, do you have iron 2+, or do you have iron 3+? Do you have a specific oxidation state of your species? So it's one of the very few techniques that's specific to do that. The other reason people like electrochemistry is just because it's cheap. So in the lab this semester, the electrochemistry experiment is one of the cheaper experiments that you're going to be able to do, where the mass spectrometers cost a lot of money, and separations instruments, HPLCs cost a lot of money, electrochemistry is pretty cheap. So you probably have learned at least a little bit of electrochemistry, right? And if you were to read a textbook, right, they would always start off talking about an electrochemical cell. And so in an electrochemical cell, you have to be able to move ions. So you have to be able to have things move between the two cells. And so the normal textbook representation of a cell is something like this, right? It's 2 beakers of water, and they put a salt bridge between them. So something like KCl, something like that. So they have a salt bridge between them. And in one beaker, they put a metal electrode, maybe something like a zinc electrode, and the other one, they'll put another metal electrode. In this case, let's make it a copper electrode. And so, these electrodes then are hooked up to a tensiostat of some sort, where we can measure a current flow as we sort of apply a voltage. So we can measure current or voltage. And so in this case, the reactions that we would be doing at the zinc cell, we would have zinc in the solution with a zinc 2+, so we would have zinc going to zinc 2+ plus 2 electrons. That balances it out. And so metal that goes to that reaction, so this is right, the zinc is losing 2 electrons. So if you lose electrons, that's an oxidation. And so in this case, the zinc electrode then is the anode. So that's where the oxidation takes place. At the copper electrode, we have an opposite reaction. So we have copper 2+ plus 2 electrons goes to copper. So right now the copper 2+, so we would have to have a solution, right, of copper sulfate, something like that, that has copper 2+ ions in there, right? And the copper 2+ ions, right, are going to go to the electrode plus 2 electrons and form plate copper onto the copper electrode. So in this case, the copper 2+, right, gains electrons. The overall reaction gains electrons. That's a reduction. And that, we say, takes place at the cathode. So this is the cathode. So this is what you find in every textbook, maybe in your Gen Chem textbook, certainly any of the analytical textbooks I have on reserve will kind of show you that. And it's very lovely. And there's nothing wrong with that. In fact, let me finish it out for just a second, and we'll write an overall reaction for this reaction would be sort of copper 2 solid plus zinc 2+ goes back and forth between the zinc solid and copper 2+, right? That's our overall reaction. The problem is that we don't really usually do electrochemistry like that. And certainly in our class this semester, in our lab class, we don't do electrochemistry with 2 nice little beakers separated by a salt bridge. Instead, in our class, what you're going to see is basically one beaker, one little vial, and we're going to stick in a screen printed electrode. And so on that screen printed electrode, we're going to have a working electrode and a little bit of a reference, and then there's something called an auxiliary electrode. We'll talk about the functions of all those in a minute. We don't have this salt bridge, we don't have these metal electrodes, and instead we have carbon. So this is the carbon right here, and that's our, again, going to be our working electrode in the experiment that you're going to be doing. And then we have what we call a reference electrode, and our reference electrode in this case is silver chloride. That's a standard reference electrode. And so which of these is the anode, which is the cathode? Well, it depends, right? What we're going to be oxidizing and reducing is going to happen here at the carbon electrode. The other one's going to be the reference electrode. But which is the anode and which is the cathode just depends on which direction we're scanning. We can both oxidize and reduce things at the carbon electrode. So sometimes it could be the cathode, sometimes it could be the anode. And so it's not like kind of the textbook electrochemistry that you see there. Okay, so let's talk a little bit about thermodynamics. This class, if you actually look at the course catalog, the class says it's titled Laboratory and Chemical Kinetics and Thermodynamics. So I want to make sure we cover some thermodynamics as far as we go. So let's start with the classic sort of electrochemical equations. Let's talk Faraday's law. So Faraday's law is just simply this, that the charge you get out of a solution is equal to the number of moles times Faraday's constant. So Q in this case is charge, N in this case is number of moles, and F is Faraday's constant. And so Faraday's constant, F, is equal to 96,485. You might have used that, again, if you've done some calculations like this before. The units on them are coulombs, which is a unit of charge per mole. But Faraday's constant actually isn't that hard to think about. Coulombs, so the charge of an electron is 1.6 times 10 to the minus 19th coulombs. So each electron, right, has that charge. And if you multiply that by 6.02 times 10 to the 23rd, right, which is Avogadro's number, right, you would get this number, 96,485. So it's not magic. Mr. Faraday's constant, he just multiplied these two other constants basically together. But we're going to see this F comes up all the time in our thing. So when we're measuring in electrochemistry, most of the time is current. So we're going to use small I to mean changing current. And current is the amount of charge that flows. So I always like to think about current flowing. It's electrons flowing, it's charge flowing. In this case, the unit then of current is an ampere. Lots of times we'll just call it an amp or an A. And an ampere is a coulomb per second. So how much charge is flowing per unit of time. And so the question is, how do we get stuff to flow? How do we get current to flow in our system? Well, the answer is, right, that we apply voltage. So we apply a voltage, right, to drive electrons, to drive our current flow. And so voltage, right, is V. My favorite definition of voltage may or may not be the one that you learned in physics class, if you're taking physics, is work done to separate charge. So you see that if I'm going to separate charge, i.e. if I'm going to make electrons flow, that's separating charge, then I'm going to have to do some work. And so a volt then is a joule per coulomb. So joule unit of work per coulomb. And so I think it's sort of interesting or useful then to think about what is the work I have to do, right, to move charge, right? So the work I have to do to move charge, right, joules, would be whatever I'm going to apply my voltage. In electrochemistry, a lot of times, just so I'm not confusing you, they use E for voltage. So E, electric field, instead of V for voltage. So I'm going to apply a voltage, right? I told you that's going to be in joules per coulomb. And now, right, that's going to be multiplied by the amount of charge I have, right, which is in, that should be big C for coulombs. Okay, so the work that I get, the work that I do, right, to move charge is just the voltage times whatever charge. Okay, so what's work in thermodynamics, right? I've been using the word work rather than using a term, right? Turns out, right, that the term that we most often end up using is delta G, right? So delta G is work, and in this case, this is the work done to measure the charge. What we really want to probably know is the work done to move on the surroundings. So delta G actually ends up being minus. So the work done on the surroundings ends up having a minus E times Q. But I know what Q is, right? I did Faraday's law, so I know what Q is. And so I can say delta G then is equal to minus N times F times E. So, so that's the basics for a definition of delta G that you may or may not be as familiar with. Okay, so we have that definition of delta G, and that relates us work to the amount of the potential that we apply. Let's go on to another definition of delta G. This one you probably already know. So that delta G then is equal to RT times the natural log of K, right? Where K here is the equilibrium coefficient. Turns out if it were at equilibrium, it's not just delta G. Is we put a little zero, right? This is the standard state. If we're at equilibrium and everything has a unit activity, right, that would be the definition for delta G0. So at equilibrium, we would get this. If we're not at equilibrium, we can write another equation, but it looks fairly similar. RT times the natural log of Q, I'll get back to Q in a minute, times RT times the natural log of K. So what's Q? Q is the same thing as K. It's still reactants to their powers over products, right? To whatever their coefficient power is. But it's their instantaneous concentrations, not their equilibrium concentrations, right? So this assumes, K assumes that we're at equilibrium. Q is the same, you know, if you had the balanced equation, you'd write out Q the same way that you would write out K. But instead of taking assuming everything was at equilibrium, you would just look at a given point in time, an instantaneous point, and say, okay, the concentration is 1, where at equilibrium it might have been 1.5 molar, you know, or something like that. Okay, so now we have two definitions for delta G. One definition, two definitions. They can't be different than each other, so what we can do then is take them and put them equal to each other. So we can say minus NFE is equal to RT times the natural log of Q minus RT times the natural log of K. And if we were to figure this out, we would be able to simplify it down. And if we simplify it down, we end up basically getting E cell, that's for the cell, is equal to minus RT over NF times the natural log of Q plus RT over NF times the natural log of K. Turns out that we're going to give this a term. We're going to call this E0 again. This is the standard electrode potential. And so this is the standard electrode potential. So the form of this equation that you most often see is this. E is equal to E0 minus RT over NF times the natural log of Q. Again, reactants over products. So what have we just done? We've just used thermodynamics to derive the Nernst equation. And again, this is an equation that many people have seen, but maybe didn't know that it came from delta G. And so everything that's driving electrochemistry, again, are forces in delta G. And so delta G, again, determines what the equilibrium coefficient is going to be. That determines where your, what potential things are going to happen at. So this equation then, right, basically relates, because Q, right, is concentrations, it relates concentration to potential, or potential to concentration, maybe the other way around. So that's the Nernst equation that people use a lot. Again, N in this equation usually is a number like 1 or 2 or 3. So if you have, you know, just a standard 1 electron process, N would be 1. But if it's, you know, it takes 2 electrons, N would be 2, etc., etc. Okay, so now that we've talked Nernst equation, I probably just erased the equation I wanted. But let's talk about spontaneity. So when is something spontaneous for delta G? Hopefully you answered to yourself that things are spontaneous right when it's negative. So if you have a negative delta G, then you're going to have a spontaneous reaction. Well, if delta G is equal to minus NFE, to get it to be negative, right, that means we want a positive cell voltage. So if E or E0 is positive, that's going to be a spontaneous reaction. So that's going to go spontaneously. So it turns out that you can find tables in a textbook of basically just, and they almost always list them as reductions. And so it'll give you something like, this is the reactions we looked at before for the first example. Copper 2+ plus 2 electrons goes to copper solid. And it'll list in this table a standard E0 for these. So it's like, that one is like plus 0.337 volts. Then in the same table, you would find the reduction of zinc 2+ to zinc solid. But in this case, it tells you that the reaction is minus 0.403. So this, right, is spontaneous. This is a spontaneous reduction. But this one is not, right? That one would be a spontaneous oxidation, but it wouldn't be a spontaneous reduction. So that's how to interpret the table. All the ones with positives are spontaneous reductions. All the ones with negatives would be a spontaneous oxidation. But you would have to apply a voltage to get the reduction to work. Okay, so when we use our electrode in our experiments that we're going to do in the lab, we're going to have 3 electrodes. So I already kind of hinted at the first 2. The one where we actually do Faradaic reactions, that one's termed the working electrode. So sometimes I just use WE. And in our experiment, it's going to be carbon, but it doesn't have to be. It can be a variety of things. We have a reference electrode, and so the reference electrode is used to measure potential against. So it turns out, especially if you take physics, you would know this, right? You can't just measure voltage with one line. You can't just like touch something and go, it's 3 volts, right? You always have to do a voltage difference. We can't measure absolute voltage. So if you take physics, electronics, they always have a ground, right? Well, in electrochemistry, instead of having a ground, we have a reference electrode. And that's just a reaction that's at a known voltage that we can measure against. Okay, so that's really all we need for electrochemistry, but it turns out that we typically have, this is electrode 1, electrode 2, a third electrode. This is called a counter electrode, or sometimes it's called an auxiliary electrode. Those are 2 names for the same thing. And this electrode is used to run current. So it turns out we want this potential of our reference electrode to stay the same. No matter what I apply, I want it to stay the same. Well, with the counter electrode, But I need to run current, right, through my system. And I don't want to run a lot of current through my reference electrode or else it might change the potential. So we have a counter electrode, which is going to allow us to run lots of current without having to run very much through this reference electrode. So we typically like to set up our experiment like this. We like to set it up so that our working electrode, this is my generic electrode, is pretty close to my reference electrode. And then I don't really care where my counter electrode goes. It can go really anywhere I want to put it. It doesn't matter. The reason these two need to be close is because a solution is like a resistor. So there's some resistance to ions moving around in solution. They don't always want to go. And it turns out that we need to compensate for that. And so all of the resistance that's between the reference and the counter is compensated for. Give it a big R. But the little bit of resistance that's between the working electrode and the reference is not compensated for. So we need the reference to be close. We don't care where the counter electrode is. Typically, if you look at our screen print electrodes, that counter electrode is really large. It's the large one on the bottom. Again, we can run a lot of current. It's not going to hurt it. The reference is just a tiny little dot that's next to the working electrode. If we don't do a good job of this, what happens is what's called IR drop or ohmic drop. And so when we apply a potential, what we really get is whatever we applied minus IR drop for the solution. So this is the current that we get times the uncompensated resistance. And so if we have our electrodes really far apart or have a highly resistive solution, the E that we're actually applying isn't going to be what we thought we applied. It's going to be reduced by that amount. Okay, so the last thing we're going to think about today is the fact that, unfortunately, this is not the only current. Faradaic reactions are not the only thing that happens at the electrode.